In this video I'm going to prove that the Petersen graph is not Hamiltonian. So first let's consider the definitions. So a Hamiltonian cycle in a graph is a cycle that passes through each vertex exactly once, and then a graph is called Hamiltonian if it has a Hamiltonian cycle. So now we have the Petersen graph. So it's defined like this, like simply by drawing it, like it has a external pentagon, internal pentagon, and the crossing edges, 5 crossing edges. So in total it has 15 edges and 10 vertices, and the degree of each vertex is exactly 3. So the main theorem that I'm going to prove now is that the Petersen graph is not Hamiltonian. We consider now separately the external pentagon and the internal pentagon. So let's just draw this illustration this way. So let's say that we separated the vertices of this graph into 2 parts. So this would be the external 5 vertices. This, let's say, would be the internal 5 vertices. Okay, so because a Hamiltonian cycle, we prove it by contradiction. So the proof is by contradiction. By contradiction. So we suppose that the Hamiltonian cycle exists. Suppose Hamiltonian cycle exists, and we will arrive at a contradiction. So we consider how this Hamiltonian cycle goes through external and internal vertices. So because it's a cycle, it must enter and exit. So if it enters the external vertices, it must exit, not necessarily from the same vertex, but it must exit somewhere from the external vertices at the same time. So the same time that we enter the external vertices, we must exit the external vertices, right? So basically the number of edges between the external and internal vertices, so not inside these 2 sets, but between them, the number of these edges must be even. So the number of edges between these sets, between the not brought incorrectly, external, like this, between the external and the internal vertices must be even. So in total we have, looking at the graph, in total we have 5 these crossing edges. So we call this crossing edges between external and internal. We have 5 of them, and the even number of them must belong to the Hamiltonian cycle. the number of edges must not the number of edges, but the number of edges between external and internal vertices belonging to the Hamiltonian cycle. That's what I meant. In the Hamiltonian cycle. In the Hamiltonian cycle must be even. So in total we have 5 edges. So the only, like, it cannot be 0. 0 is only even, is also even, but it cannot be 0, but because then we would visit only the external or only the internal vertices, but we must visit all vertices. So it cannot be 0, it must be even, but in total we have 5. So there are only 2 cases. Either this number, so the number of crossing edges in Hamiltonian cycle, either it is equal to 2 or it is equal to 4. There are only 2 possibilities. So let's consider these cases separately. So if so case 1, so case 1, when the number of crossing edges in the Hamiltonian cycle, the one that we consider that exists in the Hamiltonian cycle, we already fixed it. Like, we suppose that it exists and we fixed this Hamiltonian cycle. In the Hamiltonian cycle is equal to 2. So in this case, basically, so again, this is external, internal vertices, so there are only 2 edges. So this means that all the edges here must be visited by a single path connecting these 2 vertices, right? So all the vertices here, so this should be a path that visits all external vertices, and this should be a path that visits all internal vertices. So this is, like, in total we have 5 vertices in each of these sets. So this should be a path of length 4, like 4 edges in this path, and then it goes to the other side. And here it's also must be a path of length 4. Okay, so if you go, like, if you look again at the Petersen graph, let's draw it again. So it looks like this. So so the only way to have, so let's look at the external vertices. So the only way to have a path of length 4 is like this. So this would be a path of length 4. I mean, it can be, so this is the edge that is not visited. So up to the, like, it's the same up to rotation. So like, without loss of generality, we can say that this is the 4, this is the path of length 4 here. This path is here in the external side. This is the edge that is not visited. So then the 2 crossing edges are this one, and then like, we simply see that the internal one doesn't have a path, of length for connecting these two vertices. So like if we, like from this vertex, we can, like there are only two possibilities where we can go. Either we go here and then here, and so here, here. So this is a path of length 2 only. These two vertices remain unvisited. Or we go here, 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 and this is a path of length 3, so this vertex remain unvisited. This vertex remain unvisited. So we see directly that this case doesn't lead to a Hamiltonian cycle. Okay, so this case is finished. So now case 2. And the number of crossing edges in the Hamiltonian cycle is equal to 4. So in this case, external, internal vertices, so we have 4 edges, 1, 2, 3, 4. So first we notice that like all these 4, so we consider the ends of these 4 edges. So we notice that these 4 vertices must be all different because there are no, like the crossing edges, they don't, if you look at the Petersen graph, the crossing edges, they all have different ends in both internal and external set. So like the crossing edges, there is no situation where 2 crossing edges come to the same internal vertex or the same external vertex. So these 4 So all these 4 vertices must be different, but in total there are 5 vertices in each set, right? So there is only one remaining vertex that is not connected to a crossing edge. So one here and one here. So, but this remaining vertex is it must be visited by the Hamiltonian path. So the only way, the only way for it to be visited is through it must be connected like this to 2 other vertices in this in the same set. And without loss of generality, we assume that these 2 vertices, and the 2 remaining vertices must be connected to each other like this, because because there is no other way for them to be visited. So because on the Hamiltonian path, okay, let's remove this edge for now. So on the Hamiltonian path, so it passes through this. The only 2 vertices remaining in this set are these 2. So they cannot be connected to any of these 3, because the Hamiltonian path is already passed through these 3 vertices. So they must be connected to each other. That's the only way for them to be a part of the path. So now the same logic applies to the other set, but it could be different. vertex here. So like this remaining vertex, it could be connected to not necessarily to these two, but for example to these two or some other way. But so let's but knowing this configuration already from one set, so let's consider this on the picture of the Petersen graph. So we have again the Petersen graph. So and the external, the configuration in the external vertices is that we have a path of length 2, like this. Without loss of generality, up to rotation, we can assume that these are these edges. So these edges are here, and then the third edge is the two remaining. So these three edges highlighted are like belong to the Hamiltonian path, and then we have the crossing edges. So this edge, and these two edges. Yeah, so now basically what we conclude is that, for example, like this vertex, like it must be visited by Hamiltonian path, and the only way for it to be visited, so it cannot be visited by this edge because this edge goes to a vertex that is already visited, right? So the only way for it to be visited is to have the two remaining edges to belong to the Hamiltonian path, these two, and this basically creates a contradiction, because then we have this cycle of length 4, this cycle instead of the Hamiltonian path. So like these 4 edges already form a cycle, so they cannot be part of the Hamiltonian path, and from these remaining vertices there is nowhere to go. So this is also a contradiction which concludes the case 2, and also concludes the whole proof. So the Petersen graph is not Hamiltonian.